So today we'll move into chapter 6 and talk about inference. And as you'll see, there are two classes of inference algorithms. There is exact inference and there is approximate inference. And today we're starting with exact. And even within the class of exact inference algorithms, you'll see that there are two paradigms. One is based on the concept that's called variable elimination, and the other is the concept of conditioning. So today we will start with variable elimination. And this paradigm is actually captured in two chapters of your book, chapter 6, which we'll start today, and then the following chapter 7. Chapter 6 provides the basic variable elimination algorithm, and chapter 7 gives a more sophisticated version of it. So we'll start by motivating this. So variable elimination is a very simple computational paradigm. You can think of it intuitively as follows. So you have a model, let's say you have 100 variables, and you want to compute, let's say, the marginals over 3 of these. What you really do is you take the model and start removing variables from it, with the guarantee that if I remove a variable, then the previous model and the new model are equivalent as far as answering questions about the remaining variables. Right? So you had 100, you removed, now you have 99. As long as your questions are about the other 99, both models are the same. So you can use this repeatedly and keep eliminating variables until you eventually have only a model over the variables that you're trying to compute the marginal over. That's pretty much how it works. And the whole interesting thing about variable elimination is that sometimes you can do this efficiently. Let's see this a little bit more concretely. So what we have here is a Bayesian network, fully specified. Here's the nodes. We have 5 of them, and therefore we have the corresponding 5 CPTs. And realize here that we're going to use this format for CPTs basically uniformly in this chapter. We have to be somewhat disciplined on how we portray CPTs because they're going to be the basis for our inference algorithms. So for variable C, given its parent A, this is what we have. We're going to list the parents and then the variable. And we're going to use this notation, big theta C given A, to represent that particular CPT. And then we list here all combinations. So it's just tabular form. We've seen this before. Look at D given BC and so on. All right, so here's the Bayesian network. Here are the 5 CPTs for it. Now we know from previous lectures how to construct the joint distribution for this particular network, right? And here's how it looks. Let me remind you, for example, if you're trying to get the probability for the very first row, that's where every variable is true, all you have to do is go back and you pull a number from each one of these CPTs, right? And which number do you pull? The one for the row that's compatible with the big guy we're trying to do. So we had the row in which everything was true. So in this case, you're going to pull 0.6 from here, 0.2 from there, and so on, and multiply them. Good. So this is now the joint probability distribution. So now suppose that what I want to do is compute the marginal over the variables DE. All right? So that means I have to eliminate the variables A, B, and C from that joint distribution to get this particular marginal in this particular case. And that process of elimination, we also call it summing out or marginalizing the variables A, B, and C, again, to get the marginal over that. So now we're going to see it visually, and then later we'll write the equations or the formal definition and tell you some about the properties of this summing out. Okay, I want you to visualize this because this is going to be bread and butter of a lot of things that are going to be happening. So to sum out a variable, say A, from a distribution is to produce a marginal distribution over the remaining variables, right? And look how we do it visually. You look at those rows that agree on every other variable but A. So in this case, because all of the variables are binary, there's only 2 in this case for this particular instantiation. True, 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 right? and A varies, true, false. And we simply merge these two guys. How do we merge them? We add up these two numbers, and we drop the reference to A. That's what we did. We take these two rows basically and turn them into that single row. So if we have this joint from before, and we go ahead and sum out the variable A, what are we going to do to the table? We're going to slash its size by half, right? By simply taking these, every pair of rows that agree on everything but A and just collapsing them together. That's basically the process of summing out. And again, the guarantee here is if you started with the original table representing distribution PR and the new distribution is PR prime, then you get this for any event alpha which does not mention the variable A. Here's the key thing. So the way we showed it so far is kind of tacitly assume that you're going to go build the joint distribution and then start taking variables out until you get the margin. Computationally, it will be problematic, right? You won't be able to construct the joint. So the key thing now we're going to see is we can actually perhaps do the exact same thing without ever constructing that joint, right? And sometimes we can even do it very efficiently. We're going to know a lot about this. So how is this going to happen? Okay, we're going to make few observations, and you're going to see how we can do the same thing without ever constructing the joint. The idea is the variables can sometimes be summed out while keeping the original distribution and all successive distributions in some factored form. Now, how would that happen? To state this observation that is really the key insight behind variable elimination, we need now a little bit more on notation, sharpen our notation. So we need the notions of a factor, and then, as you see, a couple of operations on factors, and then we will formally state what's going to happen with variable elimination. But what is a factor? A factor is a mapping from variable instantiations to numbers, right? So we've seen those. CPT is a factor, right? The factor, though, is more abstract. A CPT really was a conditional distribution. In this case, probability of D given BC. But a factor could be a joint distribution, like here. And it doesn't have to have very clear probabilistic semantics. Literally, it's just a mapping from variable instantiations into numbers greater than or equal to 0. What you'd see in variable elimination, it's going to be really an algorithm that operates on factors. It starts with a set of factors and start doing 2 operations on them, and then at the end, it gives you back a factor which contains your answer. In variable elimination, for example, when we start, all of the factors are CPTs. They have this particular form. But then the algorithm starts working and producing these intermediate factors. At the very end, what it gives you back is a factor that represents the joint distribution. But in the middle, it's not clear, immediately clear what the meaning of these factors are. Right? So once more, it's just a mapping from variable instantiations to numbers. And since we're going to be working a lot with them, we also will use some further notations. So if f is a factor, then vars of f are the variables mentioned in the factor. Sometimes we will write this to mean a factor over the variables x1 through xn. And again, remember our notation. This guy is a set of variables. This guy is an instantiation of these variables. So really a factor is mapping these small x's into numbers. Sometimes we have what we call a trivial factor, a factor that only has one variable instantiation, the trivial one. You'll see this pop up sometimes. This is the notation we use for the trivial variable instantiation. So in that case, the factor represents really just a constant, just one number. For example, if you take a distribution and sum out all variables from it, you're going to end up with a factor that has this trivial row and the number. You're going to see this in just a little bit. All right, folks. So let's formally treat the sum out operation. Here's our factor. It's over a set of variables x. And my goal is to sum out this single variable from that set of variables. Now look at the notation. If I do that, the new factor will be over y, which is the set of variables x removing from it the guy that I'm summing out. Look at the notation. Here's the notation we're going to use. You're going to see this a lot next. I'm summing out the variable x from the factor f. Okay? Think of this as a table. but now it's a table over the variables y. So it's meaningful to write this. What does this guy assign to the instantiation? Small y, correct? And here's the formal definition. This is the original factor. It's over both x and y, and I'm summing over all possible values of x. That's the, if we write it in an equation, and we've seen it actually how it works, right? So b, c, d, I'm summing now the variable d, right? What happens? First two rows get merged. What do I get? Actually, remember what this was? This is CPT, correct? So the first two rows represent the distribution over D under B being true and C being true, correct? Now, if I merge these, what do I get? 1. What happens for the following two? What happened here? I gave you a CPT, correct? And I summed out the variable that corresponds to the child. And then what did you get? A factor that maps everything to 1, kind of the identity factor, right? Remember this observation. This will always happen. Anytime I give you a CPT and I sum out the child, you get a factor that maps everything to 1. I will recall this observation later to quickly prove a technique that actually we'll do towards the end of today's lecture. Okay, so this is summing out. And a couple of observations on summing out. One is the order of summing out doesn't matter. So if you have a factor, you sum out x, then y, it's the same as summing out y and then x. So we will find ourselves not having to specify the order. We will just write sum out x, y, and leave the order out. Okay? As far as terminology, when we sum out the variable x out of the factor, we would say that we marginalized x or projected on the complement. So in this case, we're assuming that the factor is defined over x, y. So we summed out x, that means we marginalized x, or we projected over y, right? Because the resulting factor will be over y. So projecting over y or marginalizing x. All right, so there is pseudocode in your text for implementing the sum out operation from a factor. It's straightforward, but the one observation I want to make here, because we're going to recall this when we talk about complexity later. If you have a factor that has w variables in it, right? Then summing out any variables from it can be done exponentially in the number of variables. Actually, summing out can be done linear in the size of the factor. But the size of the factor is exponential in the number of variables. One more operation on factors, which is multiplication. And then we'll find out that multiplication together with summing out will allow us to nicely phrase the algorithm of variable elimination and again communicate the main insight behind it. So what is factor multiplication? Again, concretely initially, and then we will look at the equation. Here's one factor over the variables b, c, d. And here's another factor over DE. They could be over arbitrary variables, and I want to multiply them. Now, what does that mean? Multiplying two factors amounts to generating a factor over the union of their variables. So I take BCD, and I take DE and take their union, and that's what I have here. Now I have to populate this factor, right? Pretty simple. You go to the row. And since this set of variables is a superset of that, if I have this row, there is precisely one row here that's compatible with it, correct? I pull the number from it. And similarly, there is precisely one row here that's compatible with it. I pull the other number and multiply them. That's basically it. Let me show you the equation, and then I have to ask you a question. Because now that you have this, we can state a result that we did before now, maybe more compactly. First notation, we're talking about a factor f1 over the variables x, another factor f2 over the variables y, and now I want to multiply them. So the result will be over z, which is the union, correct? And look at the notation. Just f1, f2. And then now I can say, what does this guy say about the instantiation z? Okay, now look what this says. It says, whatever the first says about x multiplied by whatever the second says about y, where the instantiations x and y are compatible with z. We've seen this notation briefly before, but now we revisit it. Okay? This means the two instantiations agree on their common variables, right? and then y is compatible with z. Now, factor multiplication is commutative and associative. That means the order also doesn't matter. So we can just say, here's a bunch of factors, multiply them. We don't have to specify the order. We're good? Okay. Now I'm going to ask a question. Do you guys remember the chain rule for Bayesian networks? When I give you a Bayesian network and I say, show me the distribution that it actually induces, correct? We just practiced it initially. Can you phrase that thing now using the notion of factors? I give you a Bayesian network. That Bayesian network is made up of CPTs, correct? These CPTs are the factors. And I say, what would be the joint distribution that corresponds to that Bayesian network? We had a verbose way of explaining that. Now we have actually a very easy way to explain that. You want to guess what that joint distribution will be? Anybody? Yes. Exactly. In fact, if you take the factors, here's the concrete example we've seen. Here's the Bayesian network. Here are the 5 factors. And look at our notation. We have this nice notation for the CPTs. That's a factor, right? You just take the product. That is the joint. Okay, but again, we'll see now how nicely this will play. The nice thing about variable elimination that you're going to see, which is not easy to see for other algorithms, is that usually in algorithms, I describe what the computation is nicely using an equation, but that doesn't correspond to the code. There is quite a bit of a distance between the description of the computation and how we do it computationally. Not in variable elimination. I can, in one line, really describe what's going to happen in computation, and you're going to see it in just a second. But let me actually go back to the slide I just skipped on the complexity of multiplication, because I also want you to remember this. So if I am multiplying a bunch of factors here over x1 through xm, each factor is over the corresponding set of variables, and the resulting factor will be over the union of these guys, right, over z. So if we let w be the size of this z, then this is the complexity. Same thing, it's exponential in the number of variables that I have, but m is the number of these factors that I'm multiplying. And here's the pseudocode, straightforward. Here's our now reward for the notation that we introduced. Look what's going on now. What do I know? I have the Bayesian network that I've just seen over the 5 variables A, B, C, D, E. I want the marginal over D and E. Now, what did we say? We have to sum out A, B, C. From where? From the joint. What is the joint? It's just the product. And now I'm summing out ABC. Look how beautifully this described it is. This is it. Multiply all of the factors and sum out A, B, C. Now, you're going to say, okay, looks good, but that's not an algorithm. By the time I do this, I'm dead, right? I can't do this. Okay, here's now we get to the bottom line behind variable elimination. Suppose that I have 2 factors, f1 and f2. I'm trying to multiply them and then sum out the variable x from that. Now, if variable x appears only in f2, doesn't appear in f1, look what I can do. I can sum out x from f2 and then do the multiplication. I get the same result. I don't have to multiply first. You guys get it? Okay, look now how far we're going to take this. Suppose now it's a little bit more interesting. I'm actually multiplying a bunch of factors, f1 through fn, right? And I want to sum out x from the result. Now, suppose in this case that, as before, it only appears in one of them, which is fn, then I can do this, right? But realistically, that's unlikely. What if x appears in 2 of them? Let's say fn minus 1 and fn. Look what's going on here. So same situation here, except now x appears in the last 2. So what do? I can just multiply these 2 and sum out x. If you think of f1 through fn as the factored form of the distribution, What is this doing? Delaying the multiplication. It's saying you want to get rid of x, I'll do only as much multiplication as needed to do that. And as you see now, if you play this carefully, you get very interesting guarantees. So I'll tell you right now where we're going to get with this. One of the main computational guarantees that you get when you do inference in Bayesian networks and probabilistic graphical models more generally is this notion of the tree width guarantee, which says that if you have a graph that has a tree width of W, then you can do inference linear in the number of variables and exponential only in tree width. This is like the most celebrated result in this area of research in terms of computation. And tree width, we alluded at before, we're going to talk more about later. It's a measure of tree likeness. It tells you how close a graph is to a tree. You will get that using this technique. Let's take this one step further. If in general, this was two of them, but if in general I have a bunch of factors that are in product form, I'm looking at the product and I want to say remove x, all you have to do is find the subset of these that mention x, multiply those, and sum out x. Okay? Let's take an example. Now how we're going to use this to do inference. This is a concrete example. And here I have a simple Bayesian network, A, B, C, chain, and the corresponding CPTs. And what do I want to do? I want to compute the marginal over C, right? And how am I going to do this? I'm going to first eliminate A and then eliminate B, correct? Okay, you tell me what's going to happen in this case. I want to eliminate A. Visualize it like this. You have the CPT sitting on your table, right? And I'm going to say eliminate A. What are you going to do? You're going to find the guys that mention A. What do you do with them? Multiply them. Sum out A. And then what do? You go to the table, you throw the guys that you multiplied and put the new guy in. So in this case, how many mention A? Two of them. This and that, correct? I multiply these two guys, and when I sum out A, what do I get? I get a factor over just B. It replaces these two guys. Right? Here it is. I took this guy and that guy and multiplied them. And look what we're going to do now as far as notation. When I multiplied these two guys, what did I get? This table. Look what I put in here. The product. We're going to keep a trace of the operations we're doing as we're performing this. And then what do? I sum out A from this guy. What do I get? This table over B. And look what happened here. This tells you where this factor came from. All right? You'll see the beauty of this in just a second. So now I have this factor, correct? And that's where it came from. And those are the numbers. And remember, the other factor I have is now this guy. So if I want to eliminate B, this guy mentions B. This guy mentions B. So I have to multiply them again. Correct? And then sum out B from that. So here it is. I had this and that from before. I want to sum out B, multiply them. I got this guy. So it's a factor over B, C. And this is the trace of it. And then I'm going to sum out C. Sorry, I'm going to sum out B from that, and then I get this. That's our final result. That's the marginal over C. And look what happened here. That's how I got it. Let's look now at the pseudocode because we're going to get to complexity, and there is a key observation here that we have to make, that you have to pay attention to. Otherwise, you will not get the best performance out of this algorithm. So here's the code. And the style here is, it says variable elimination PR1 because you're going to have variable elimination PR2 and I think variable elimination PR3. So we're going to have versions. We're going to make this more sophisticated. The input here is N, the network. Q are the variables that we want to compute the marginal over. And pi is the order in which we're going to eliminate the variables. The notation here is pi of 1 is the first variable to eliminate. Pi of 2 is the second variable to eliminate, and so on. Set S contains all of the CPTs for the network, right? And look what I'm doing. for I equals 1 to length of order pi. I am collecting all the factors that belong to the set and that mention this particular variable that I'm about to eliminate. Right? I take their product, and what do? I sum out that variable. What do I get? This f sub I. And then I replace all factors f, k, and s by, listen you guys, just what we talked about. Why we're putting it here? Because now we're going to reason about the complexity. And then I'm done, right? And what's going to happen when all of this when this loop finishes? You're going to be left with a set of factors that only mentions q. Now, in the example we did, we were left with one factor. That doesn't have to. You could be left with a bunch, which means that the marginal over q in that case is in factored form, right? But this here says, let's multiply them because I want to give you one factor back. Now, the key thing about this algorithm and about its complexity is the following. The main loop here is this. This loop will execute how many times? The worst case, n, which is the number of variables. Inside it, what's happening? There's line 3 and line 4. Complexity-wise, are they different? The amount of work that's happening on line 3 versus line 4? Here I'm doing a multiplication, and the resulting factor f is over a set of variables. And here's I'm doing a sum out. What's the difference between f and fi? One variable. So we're going to assume here that we're going to use w to mean that w represents the number of variables in fi. So the complexity of this is exponential in w. And that's also exponential in w. Let me just make one more observation here before we state the complexity a little bit more sharply. In the example that we had, which had 3 variables, a, b, c, we went ahead and computed the prior over c by eliminating a and then b. You could have eliminated b and then a, right? We said it doesn't matter, right? The order of summing out doesn't matter. It does not matter as far as the answer. It does matter as far as how much work you end up doing. All right? That could be eventually the difference between linear and exponential work. And this example just illustrated, not that dramatically, but what we did in this case is eliminate a first, then b. Look what happened. When we eliminated a first, we multiplied these two guys. That's over 2 variables, correct? We summed out a. This final thing is over 1 variable, right? Which is b. And then, when we eliminated b, we multiplied this guy with that guy. We got a factor over bc, correct? And we summed out b. Then the final thing was over also 1 variable. So if you want to look at this guy here, on line 4, the largest factor that I ever constructed was over 1 variable. That's the thing I want to remember. When you execute this algorithm using a particular variable order, what is the largest factor you construct here? I want to keep track of that because that's going to be what's going to characterize the complexity of this algorithm. The loop is n, and that's the w. In this case was 1. Now look at the other order. In this case, and now I reversed the order. I eliminated b first and then a. Look what happened. If I do that, eliminating b, I have to multiply these 2 factors first because these are the 2 guys that mentions b. Then I get a factor over 3 variables. I eliminate b, then I get a factor over 2 variables, a and c. Right? And then eliminating a, I multiply that with this guy, da. So, in this case, the largest factor I had to construct in the process is over 2 variables, not 1. So if I'm looking at this code and I'm telling you, keep track of the largest factor you constructed on line 4, and one of them will be 1 and the other will be 2. That's the guy we're going to keep track. In fact, that number, which is the largest number of variables in fi across all iterations of the loop, we're going to call it the width of the order. Remember that number. The notion of width is going to be with us in a lot of places. The width of this order is 1. The width of this order is 2. Okay, now we can write an expression about the complexity. If you discount the very last step, there's the loop finished, then we multiplied all remaining factors. If you discount that last step, then the complexity is just this, right? W is the width of the order, N is the number of variables, that's the complexity. If you do the multiplication on the very last line, in the worst case, that's this guy. Right? So this is actually the complexity of this algorithm. If you assume that the Q has a small number of variables, I'm computing the marginal over a small number of variables, this guy goes away, and then you're left with this. In fact, when people talk about variable elimination, they show you this complexity result. Right? Linear in the number of variables, exponential in the width of the order used. This thing that I'm going to show you now is a simulation of variable elimination at a symbolic level. We'll do two simulations. One I will do for you. The other one you will actually discover for me when we come back. The goal of this emulation is to figure out the width of the order that I'm using. Right? Okay. Here's our set of variables, a set of factors, S. Initially, all of them. And look what's happening here, the elimination process. The first thing I'm going to do is eliminate B. Right? What do I do when I eliminate B? I have to multiply all factors that mention B and sum out B from the result. Here they are. There are two factors that mention B. These are the two. I multiply them, sum out B, and I get the factor I'm going to call F1. So F1 is over which variables? A, C, D. Now here's my set of factors. I threw these two guys out from this and I replaced them by that guy. We're good? But look what I want you to do. I want you to keep track of W on this side. What was this? 3. Correct? Okay, now I eliminate C. Then I look at these guys and see the factors that mention C. How many of them? This guy, and that guy. 3 of them. And here they are being multiplied on this row, and C is being summed out to give me F2. Correct? I throw them out and I replace them by F2. Now what do I have? The set is 2 factors only. And I'm keeping track of W, which is 3. We're good? And you keep going. Now you sum out A, you get this, and here's W, and then you sum out D, you get this guy, and here's W. So that's the final result, is the marginal over E. And what is the width? The width is 3. The point here is we figured out the order width without actually executing variable elimination. Okay, we're going to do actually something even better next. We're going to do this at the graph level, not even at the factor level. And you're going to discover this for me. All what I'm doing here is I'm telling you I am doing variable elimination and I'm using this order. Can you help me find out the width of that order, because I want to characterize the complexity of this run. But this is leading into, now that we have this and we understand it a little bit more, and then I'm going to tell you, actually, can you find me the order that will minimize the work? And then we have to know what to do in that case. But we need to build the intuition to get there. Okay, here's what we're going to do. We're going to take our 10-minute break. But when we come back, look what I want you to do. I want a version of this that's done at the graph level. What does that mean? Let me tell you what the graph is. If you give me a set of factors, I will talk about something called the interaction graph of these factors. And what is that? An undirected graph where every node is a variable. And if you have a factor F, then you pairwise connect all its variables. That is, the variables of a factor, you make them a clique. Here it is for our set of factors. This guy. We had 1, 2, 3, 4, 5 factors, and the variables are A, B, C, D. We did it. And what did we do? A, nothing here. B, A, then I have to connect B, A. There is an edge. C, A, I did it. Now, what is this? B, C, D. B, C, D, I want to make them into a clique. So pairwise connect, 3 edges. And then EC. This is the interaction graph of that. We're good? Okay, here's the query for you, which we'll figure out when we come back. I want to just give you the interaction graph. I don't want to give you the factors. I want to give you just the interaction graph. and I tell you I am about to do variable elimination using this order, find its width. Tell me what will happen. What would be the complexity of running variable elimination using that particular order? The only thing I'm going to give you is the interaction graph. And once we do that, then we'll set the stage to the question that you asked. What would be a good order versus bad order? All right, 10-minute break, and we will tackle this problem when we come back.